So what is the purpose of the talk? Is to show that we have two standard design principles for exploration that we all love, and they are probably seriously flawed in a lot of situations that we have to deal with. So that's kind of the main message of the talk, and we're going to offer some alternative, but yeah, like more about that later. So the purpose of the talk is to bash certain algorithms, and for this we're going to use a simple setting, and the model for the simplest setting is on this slide. You have a set of actions, and it's a finite set of actions. Okay, so you have A, and you can imagine that you just have numbers in that from 1 to, I don't know, K or something. And actually in those set, you have this, like let's denote the elements of X, and for each of those elements there is an unknown distribution. It's a payoff for reward distribution, and in each round you're going to choose one element of this set. You observe a reward from the distribution that corresponds to that. We call it arm or action that you chose. And your goal is to collect as much reward as possible. And let's say the total number of rounds is n. So that's the basic set. It's like a simplified reinforcement learning setup when you don't have state. Right? What can be simpler than this? So two examples of this setup. So in the first example, you just have, in the action set, you just have the numbers, and there is no relationship between the actions. So all these distributions underlying the actions are, just maybe Bernoulli distributions. There is no relationship between these distributions. So learning about one distribution doesn't give you information about the distributions of the other arms or actions. Okay? So that's the classic K-arm bandit problem. You pull an arm, you observe the reward, you didn't learn about any of the other arms. So what is the second setting? So that's called the linear bandit setting. In that setting, the reward that you observe is equal to the inner product of the action. So the action actually lives in a d-dimensional space. It's a feature vector of the action that you chose. You have a feature vector, and the feature vector of the action that you chose is multiplied with these unknown parameters. That gives you the mean reward, and that's contaminated with noise, right? And so eta t is just this noise variable, so it's zero mean. Maybe it's IID in the simplest setting. It's IID, zero mean, unit variance Gaussian. That's the setting that we're going to look at. And still you want to maximize your total reward. What is the difference between these two settings? So here, if you pull an arm, you're only learning about the underlying distribution. Here you are learning about the shared parameter. So you're learning about the payoffs of the other arms as well. You can generalize from one arm to the next arm by using the prior information that you have about the structure of the problem. So that's like a nice, a generalization of the simple K-arm bandit problem, because it allows you to generalize from one arm to the next arm, so you can potentially learn with many more arms than it would be possible in the K-arm bandit setting, when you have to try every single arm in order to learn about that. So that's the premise. So you assume that these may be small. So you only have a few parameters to estimate, you have many arms, and you want to somehow exploit the structure and learn. Okay, so we are going to need some notation. So we're going to be in this setting, so this is called the linear bandit setting. Any questions for this? Good. So we're going to need some notation, which is that I'm going to use mu of x to denote the mean reward, mean payoff for arm X. Okay? So X was just a generic arm or action and mu of x is the mean of that. Mu star is the maximum reward that you can get in a single round. Okay? And the gap between the payoffs of these two guys is going to be denoted by delta x. So that's how much you lose if you're playing action x instead of the optimal action in a single round on expectation. Good? Alright, I have 15 minutes. Is that right?
20 minutes.
20 minutes. Oh, haha. Good. So here's a little example to illustrate this linear bandit problems. So you have a bunch of interesting food items embedded in a two-dimensional space. Those are the things that you can choose. These are the feature vectors of these items. And you have a parameter, that vector that happens to point in the direction. It's all the Hasse stuff that works a lot, right? And so what's the mean reward? It's the projection of the feature vector to the parameter vector, right? So that's the mean reward. So this guy has very small reward. That's the next one. That's the next one. This is the gap between the payoff of the optimal. So that's the suboptimality gap of apple. And somehow Kit Kat tends to do really bad, really poorly. So that's the setting that we are looking at. So you don't know theta, right? Like theta could be, you know, maybe aligned with Kit Kat. Like in my world, that's how it should be. So how do we evaluate learners? So one standard measure that we use, it's like a normalized measure. Compared to how much you could have made in n rounds, how much did you make? It's called the regret. And you want the average regret to go to 0, because then that means that you are almost as good as if you knew what to choose from the beginning of time. So that means that the regret should grow in a sublinear rate. So if you divide Rn by n, that should go to 0. So that's sublinear rate. If you strengthen that and you say that I have a strategy such that for all p, not only for like p equals 1/2 or whatnot, but every small p, the regret grows at most at the rate of little o n to the p, then we're calling a strategy consistent. It turns out that for these finite and bandit problems, you can find strategies which are consistent. They have logarithmic regret, so the logarithm function satisfies this, right? So if the regret rate grows logarithmically, then for an algorithm, that algorithm would be consistent. We have these algorithms out there that people are publishing about that are all consistent, right? Like uniformly for all the problems that you can choose, the regret grows at most logarithmic. The question that we ask in general, so I'm arguing this is not an empty set. The question is how small can we make the regret? And one standard algorithm design strategy is optimism. So how does it work? In each round you're going to construct a confidence set, CT, which is a subset of RD, the feature space, the dual of that, the parameter sleeve, such that the true underlying parameter vector is included into that confidence set with high probability. So based on the data, somehow you cook up this random set, and with high probability, the unknown parameter lives in this set, and then you solve this joint maximization problem. So you choose the best parameter vector for every vector, x in your action set, and then you get a score for every action. And then you choose the action with the highest score. So you're optimistically viewing at every single action, how much could the payoff be if the parameter vector lived in this high probability confidence set. You try to make the confidence set as small as possible, but it should contain the parameter vector with high enough probability. That's kind of the game that you're playing. And then you just choose the highest scoring action. So for finitely many arms, you can do this. It's a little computation, assuming that the confidence set has some regular shape, like it's an ellipse. Most of the time, it's an ellipse. Then you can just compute this, and it's a little computation. So why does it work? So why does this optimism work? So you have here, so how much do you lose in a single round? So let's say you choose action 80 in this manner, in some round. So that of 80 is like how much expectation you choose in this round. And you can just write it this way. And here we have this inequality. Where the only difference is that I replace x star here, x star times theta, I replace it by AT times theta tilde. Why can I do that? It's because theta is contained in this set, this high probability, right? And I was maximizing this within this set. See, theta is in that, x star is in that. So this was overall best in this set of A cross CT. So therefore, my choice, which is the overall best choice over all these possibilities, is better than this fixed choice. Right? I was enlarging the confidence set contains the true unknown parameter, and that's it. So once you have this, then you again put together the two inner products, and you see that, well, this is nothing but it's essentially the width of the confidence set in the direction of this feature vector underlying of the action that you chose. And so you just need to somehow show that over time this shrinks. And it's reasonable to expect that that shrinks because you're just learning about this direction. Like when you're choosing this action, you're exactly learning, you're exactly decreasing the width of the confidence set in this direction. So it's going to work out fine. So this is why optimism works. Okay? So it's kind of nice. So how do we construct confidence sets? Well, we realize that if you think about this problem, it's just a linear regression problem. You have the AT vectors coming in, the YT vectors you're observing. There is an unknown parameter vector multiplying the AT vectors, inner product put together. So it's and that's equal to YT in noise, so they're just least squares. Right? So you set up the least squares problem, you solve it. How does it look like? This is how it looks like. You compute the Gramian inverse multiplies the correlation between action vectors and rewards, so that's the least squares estimator. And then you can work out, like doing some math, that the confidence intervals that apply to a single action look like this. It's like an ellipsoidal confidence set that underlies all this. And C is a universal constant, and this notation here is just this matrix weighted 2 norm. And so okay, so if you do this choice, which underlies an ellipsoidal confidence, is the same as the previous algorithm, and we published a paper about this, that if this works with some C constant, and the regret can be bounded by b times square root of n, polylog n. And this almost matches the lower bound by some other guys, which is b times square root n. And well, this is a worst case bound that applies to when theta belongs to the unit ball. Okay? So the problem structure, the final problem structure of how the feature vectors are interacting with each other and the theta vector, how you're learning is kind of like obstructed. Because it's a worst case over all possible thetas within a ball. But nevertheless, this is a result. But this is kind of what typically is published. So in this work, we set up understanding the final problem structure. So problem-dependent upper and lower bound, logarithmic lower and upper bounds for this finite time linear bandit setting. So and this is the lower bound that we get. So we started with a lower bound to see how hard the problem is. So this lower bound is an algorithm-independent lower bound. It's not like that, like I take this algorithm and for this algorithm I can't improve the bound. But it's like, no, doesn't matter what algorithm you're going to choose, as long as it underlies a consistent strategy. Consistency was defined as essentially subpolynomial regret grows, like logarithmic. Then the following holds. Well, first of all, so what is this? So this is kind of like the width of the confidence set underlying action X. If you remember, we had this width, right? So that's kind of the scaling of the width of the confidence set. So we have that if you are scaling this log n, then the width squared is bounded by this quantity. No, this might seem a little bit obscure, but if you turn things around, then you can turn this into a lower bound that says that no matter how you chose this consistent strategy of yours, the regret of the strategy, if you divide that by log n, as you let n go to infinity, in the limit is essentially going to stay above a constant that depends on the theta parameter vector and what vectors you had in your action set. So there is this constant c that determines this dependence. So this means that the regret in the limit grows at least logarithmically, right? So if you reorder this inequality, imagine that's not there. You multiply this log n, that goes there. So that means that in the limit, Rn is at least this like c times this constant times log n. And then this constant kind of captures the inherent difficulty of the problem. If the theta is kind of like nicely aligned with the action vectors, then this constant will be smaller, and if it's not nicely aligned, maybe it's going to be bigger. So what is this constant? This constant actually should make a lot of sense. So what the constant says is that an algorithm that is eventually solving these bandit problems must be able to separate the optimal arm from all the suboptimal arms. So it has to use allocation counts in such a way that if it takes those allocation counts and creates the underlying Kremlin matrix for the underlying least squares problem, that kind of describes like to what extent you're gonna know, like to what precision you're gonna know your parameters for that arm, for like how much, like how big the confidence set is going to be for that arm. The width of that confidence set should essentially stay below the gap between the payoff of that arm and the optimal arm, so the underlying gap. You have to be able to separate your arm from the optimal arm. This is all what it says, right? So you have to do that, but an optimal algorithm is going to try to minimize the regret as well as keeping these information theoretic constraints. So this is like saying that you have to have enough information to learn about the optimal arm, and this is saying, but at the same time, you could do that in many different ways. You want to do it in the cheapest possible fashion. So this is like the regret, right? So how much you're losing by learning to separate all the arms from the optimal arm. That's the lower bound, okay? And then we have an upper bound, and I have like 15 seconds. That says that, well, the leaf soup is also upper bounded by the same quantity, right? So we're going to have an algorithm that is just matching exactly this. And so in the last -5 seconds, why optimism fails. So here is a little example, because that was kind of like in the title, right? So I really owe you this explanation. So the first arm is perfectly aligned with the parameter vector. Okay, so that's theta, and that's the first arm. It's a two-dimensional example. This is the second arm, and there is going to be a third arm. That's the blue arm. And these regions tell you if the parameter vector is in this region, then red wins. If it's in this blue region, then the blue arm wins. And if it's in the green region, then the green arm wins. Okay? The true parameter vector is, let's say, here. So what happens to an optimistic algorithm? What happens to an optimistic algorithm is that it goes in and constructs this confidence set, which is generally an ellipsoid, and it's going to learn that somehow this is where the arm is. Okay? And as it learns, it learns, and it's going to shrink this confidence set. and as it shrinks, the confidence set is going to shrink such that the arm, the E2 arm, is going to be ruled out. At the time it's ruled out, the algorithm stops pulling. But that is exactly the arm that is the most needed to separate these two guys. Like to know whether the parameter vector is in blue or red, because that's what makes everything shrink in this direction. So the optimistic algorithm stops doing that, and eventually you're going to get ellipsoids of this shape. And what happens is that you're going to need log n divided the epsilon squared, where epsilon is the scaling parameter, which is this gap between the payoff of the optimal and second best arm. You need this many places of x, this blue arm, to learn that it's suboptimal. Basically, you reduced it to a stupid problem. You're not using the structure. So the optimistic algorithms are not doing a good way, not making good use of the structure that they have to learn about the structure. They're not planning to use the structure. They're just like, I can be optimistic. But that's not good. So that's the regret. And the optimal regret in this case is just log n. So you can calculate this constant. The optimal algorithm, you know, like it would use E2 up to the point that this ellipsoid shrinks, and then, you know, and like you can do that in a few pulls, independently of the of where blue is. Like whether the blue is very close or not, it doesn't matter. You just pull E1 and E2 a fixed number of times, and this boundary here doesn't come closer. That's the same. Like it stops. Okay. So that's it. Basically, I have to wrap up. If you okay, so one more thing. So the standard case of optimistic algorithms is finite time bandits. And in finite time bandits, what happens is you pull one arm, you are not learning about any of the other arms. You don't need to plan for that. But here, you really have a chance of doing more, and you fail to do it. So that's the lesson, right? Like these algorithms are not paying attention to the structure. They should. There can be an arbitrary big gap. So in the previous example, if epsilon goes to 0, the gap is exponential in the limit. Or not exponential, arbitrarily large, like unbounded gaps. It's huge. The way we set these things. Okay, so Thomson sampling is going to fail for the same reason. Okay, yeah. So you have an you have a non-optimistic algorithm which is optimal, but it's not really practical. I really need to wrap this up. So I didn't tell you, but it's not really a practical algorithm. It's designed to prove this point that this is exactly the constant that determines the hardest of the problem. And the future. We need practical optimal algorithms. We need finite time guarantees. We don't have those. We don't know much about what happens with infinite action sets, contextual case, and like doing all these things in more principled ways should be possible if you ask. Anyways, so summary: optimism and Thomson sampling can fail badly when generalization is possible. So maybe we should think about other ways of designing our algorithms. And this is concerning because these ideas are really widely used in reinforcement learning as well, right? So people keep designing these algorithms without ever worrying about this. And we need new tools, it seems, to come up with things that are even better. All right, that's it. Thanks. Questions? A little bit of work time.
So this is special to the linear case.
Right.
Yeah.
Yeah.
I think you said that. What happened in Bernoulli bandits that are all independent. Yeah, but
That's right. So it's about generalization. So when you have some prior knowledge that it's possible to generalize from one action to another, then that generalization could be used to your advantage, and existing algorithms don't seem to take advantage of that, which is in a way unfortunate.
Should be the easier case, you have generalization. But
you can save a lot,
yeah.
yes. But somehow the design of the exploration algorithms have to take into account the prior knowledge as well. It's not just you apply things that worked when you had no generalization, and they're not failing. We have proofs, like their Tversky is almost optimal, but they're missing out big, and it can be an arbitrary large gap.